cutting lemons for lemonade when, ouch, juice splashes into your eye. Later, while cleaning, a drop of ammonia solution accidentally finds its way into your eye. Double ouch. Why does this happen? Well, lemon juice is acidic and ammonia is basic. Both disrupt your eye's natural pH. But why don't eye drops burn? Chemistry. These solutions are specially designed to maintain your eye's natural pH, preventing discomfort. How do they work? Well, they use something called buffer solutions, which resist changes in pH when acids or bases are introduced. Esto es Real Chem. In chemistry, buffers are essential for keeping solutions stable, especially in biological systems like eye drops. But how do we design one? Good design comes from understanding how a system works, and buffers are no different. To make one that does its job, we need to think about how it responds when we add acid or base. That's the key to designing an effective buffer. Buffers resist changes in pH when small amounts of acid or base are added. That resistance is what we mean by buffering. But how does that actually work? A buffer contains both a weak acid and its conjugate base. So if we, for example, add an acid to a buffer solution, then the conjugate base reacts with the extra hydronium ions. If instead we add a base, the conjugate acid reacts with the additional hydroxide ions. That's the key to designing an effective buffer, understanding how it responds when acid or base is added. For the buffer to work effectively, both the weak acid and its conjugate base need to be present in large amounts. But how do we choose the right buffer? In general, we select a buffer system with a pK close to our target pH. Suppose we wanted to make a buffer with a pH of 4.75 and had access to this list of weak acids. Acetic acid will be a great choice because its pK is also 4.75. That means at this pH, we'd have equal amounts of acetic acid and its conjugate base, acetate, giving us an ideal buffer that can handle either added acid or base effectively. Now, what if we needed a buffer with a pH of 4.45? None of the acids I have fit this perfectly. Can acetic acid still be a good choice? Yes. A pH of 4.45 is 0.30 units lower than the pKa. When the pH is lower than the pKa by 0.30 units, the conjugate acid form is present at twice the concentration than the conjugate base. This is not ideal. Though the buffer will be better at absorbing added acid, it will still keep the pH from changing significantly. This is what we call the buffer capacity. How much acid or base the buffer can absorb before the pH starts shifting significantly. What if we had instead chosen citric acid? In this case, the pH is greater than the pKa by 1.40 units. The conjugate base form is present at 25 times the concentration than the conjugate acid. This is no longer within the buffer capacity. So beyond just picking the right conjugate acid-base pair, we also need to think about buffer capacity. How much acid or base the buffer can absorb before the pH starts shifting significantly. In summary, the closer the pKa of the buffer and our target pH are, the better, so that even when you don't find a perfect match, the buffer can still do its job. In the end, designing a buffer comes down to making smart choices, picking the right conjugate acid-base pair, and ensuring there's enough of both to handle what's coming. Get those right, and your buffer will do exactly what it's meant to do. Keep pH steady, no matter what gets thrown at it.